So we have equivalence relations, and the equivalence relation is quite simple. It has three parts that have to be true. X are X, X are Y, and X are Y is equal to Y are X. And then you have the transitive, which is the last one, which is X are Y and Y are Z, then X are Z. Those three things have to occur to be able to say that an equivalence relation exists. So relations can be paired any ways that you want, but if you wanted to have an equivalence relation, all three of these have to do. And this is what we're going to be proving today. I challenge the class to see if they can come up with an understandable explanation of empty relation. I think they explained it well, it just didn't register with me. And they have on the next page some other parts that'll maybe help. Equivalence classes are the breakdowns of things being equivalent. How are they partitioned off to give you those? And this was a little tricky for me too, but I think it'll make sense if you see my example that we're going to come up with. But the theorem is if R is an equivalence relationship, there are classes inside that are disjointed from each other. And you're going to have to define them at times. Here's the proof for that. You can read this one, but not super impacting. Let's go to example 15, and would you please underline and take notes on this, because this one I thought was the most helpful. Let A be equal to 1, 2, 3, 4, defined in the relation X, R, Y gives you X plus Y is always even. Okay, so this is X plus Y is always even when you relate X, R, and Y. Show that R is an equivalence relation, and then find the equivalence classes. So I meant to cover this up, but maybe I'll do that right now. And then I'll just move it to kind of guide you in the video. So if you took X plus Y, if it's X R X, which is equivalence reflexive, you get X plus X equals 2X. What can you tell me about 2X? It's always even. So 2X is always even. So X R X for all X is an element of A. No matter how I combine these, X R X, 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4, those will always be even. And that's kind of cool. Symmetric, X plus Y is even. Okay? So what they're meaning with that is let's say you have X plus Y equals Y plus X. So all I did is I reversed the order of X and Y. If X plus Y is even, will Y plus X be even? Perfect, yeah. So then what we'll have then for this is you'll have Y plus X is also even. Y R X is even. X R Y is even. That was given. So Y R X will also be even. Okay? Yeah, so if X R Y is even, then you have that. I like it. Transitive. Oh, this is cool. I got kind of a little chill on this one because it should not have been that interesting. It looked completely dull to me, but how this worked out is pretty interesting. So a chill might be pushing it a little bit, but a little drama. So X R Y and Y R Z. So you have X plus Y is even, Y plus Z is even. Okay, you're defining XRY as X plus Y, YRZ would be Y plus Z. We're stating that those two are even. If you accept that those two are even, then x plus y will be some multiple. We do this in HL2 as well, 2m. And then y plus z will be 2n, where m and n are integers. Okay, so do this. Add x plus y plus z and set it equal to 2m plus 2n. I essentially just added those together, those columns. And so now I'm going to get x plus 2y plus z is equal to 2m plus 2n. Okay, then what do you notice? We'll solve for x plus z. You're going to get 2m plus 2n minus 2y, and no matter what m, n, and y are, they're going to be what? That's going to be even, for sure. And what are you saying about x and z, x plus z? What did we define it as? Even. So transitive-wise, it has to work out so that they're even. Isn't that neat? I thought that was really surprising to me how cool that was. Okay, and that's what they did here. They moved things around. They factored out the 2. We already defined x plus z was even, so that is as transitive as they get. That shows it super well. xry and yrz, then xrz. Since r is reflexive, symmetric, transitive, then it's going to be equivalent in A. Questions on that? Seem doable? So on a quiz, you do each of those 3, reflexive, symmetric, and transitive, prove those. And then they do have one more thing that they want us to do. Find the equivalence classes. And this was a little surprising to me too. Okay, if we looked at all of the ways to combine 1, 2, 3, and 4, you'd have 1, 2, 1, 3, 1, 4, right? 2, 3, 2, 4, 3, 4, 1, 1, 2, 2, 3, 3, 4, 4. There's lots of ways to combine them. But how are we defining these as the elements we keep? They have to be what? Even. So we're going to have 1 and 1. We're going to have 2 and 2, 3 and 3, and 4 and 4, for sure. Are we going to have 1 and 2? No. But we will have 1 and 3. Will we have 1 and 4? No. Will we have 2 and 3? 2 and 4. Yep. So we'll have 2, 2, 2 and 4. How about 3, 3? Yep. 3 and 4? 3 and 4? No. But 4 and 4 we will have. So they listed them all out here. 1, 1, 1, 3, 3, 3, 3, 1, 2, 2, 2, 4, 4, 4, and 4, 2. Does that seem reasonable? Because they're all even. Yeah.
So with set A is 1, 2, 3, 4, couldn't you graph them in a way that was not exclusive to this even ones that are added together? If you set A need to be even, could you just graph it otherwise?
You could, and it'd be a different relation than what they're defining up here. They're defining this relation as x plus y is even. That's what this relation is. But it could be a different relation too. It could be odd, and that would be a whole different problem. Okay, so once you have these, notice that we have 2 classes here. We have this set of 4 has what in it? And just what are the elements? 1 and 3. And these have what elements in it? 2 and 4. So what they would say is there are 2 equivalence classes. One class of pairs that have 1 and 3, and one class of pairs that have 2 and 4. So those are the 2 classes. I looked at all the other examples. This really did a nice job of showing what those classes were. When you put those together, there's one class, there's a second class. All right, I'm going to do this one too, same way. It says, let S be the set of all triangles to find the relation x comma y is the element of S as xry, X is similar to Y. So we have triangles, and we have X, Y. X is similar to Y. So if it's similar, is the triangle going to be similar to itself? Yeah, because if you had AB over AB, BC over BC, AC over AC, those will be equal to themselves, so that part works. Do you think it'll be symmetric if one triangle is similar to the next? Here's how I looked at the symmetric part. Think of a triangle that's like this, like that, and then these angles here are equal. These angles here are equal. Obviously, those two are equal to themselves. So if you have a y and you have an x, okay, and if x is similar to y, then its corresponding angles are equal. So if the little one is similar to the big one, is the big one similar to the little one? Yes. And so their corresponding angles are equal. You can do that as well. But the x r y, then y r x. So somewhere you need to, would you put a little box around this part? You need to state that for symmetric. You need to state this for reflexive. XRX for all x element of S. XRY, then YRX. And then for transitive, I did a triple. That's what I did. I just put another one out here. And then this out here was Z. Okay? And so you have, consider triangles X, Y, and Z. And if X is similar to Y, which it is, and Y is similar to Z, what has to be true of X and Z? Their corresponding angles are going to make them similar. So that is the same story for the triangle. So it's reflexive, symmetric, and transitive. And then R is equivalence relation. For the equivalence classes, if I changed any angle on this, I'll get a whole nother set of triangles. So they said the equivalence classes are the set of triangles. Thank you, smartboard. It's a set of triangles where they're similar to each other. And then there's an infinite number that you would have of classes. Let's try one where it doesn't work. Consider this one, x greater than y. Show that R is not an equivalence relation. Let's go right down to transitive. If x is greater than y and y is greater than z, will x be greater than z?
Yes.
No problem. So transitive, you've got it going. Okay, let's see about reflexive. Can x be greater than x? We're saying all x greater than y is my relation. Can x be greater than x? No. So this would be not. You can't have 5 greater than itself. And then, of course, if x is greater than y, then is y greater than x? That's a no, too. So this is, since one of those, at least one of those don't work, then it's not an equivalence relation. I'm going to have you read this one, and I think we're done going over these. That one's pretty well done. I just don't want to take the time to do it. We're going to go right to the group problems. We're going to do this one together. Okay, R is a relation in the family of lines such that x r y and x and y have the same gradient. What's the gradient? It's the slope, right? See if you can come up with something for reflexive, symmetric, and transitive. If B is a nice place to start. Any gradient, like, for example, m equal to 1/2, will have an infinite number of lines parallel in equivalence classes. You can write that however you want. Any single gradient will have an infinite number of lines that could move anywhere on that Cartesian graph. How do we do with the reflexive? Let's go through that first. Is a line with a slope of 1/2, is it have itself a slope of 1/2? It's kind of, really, we have to write that? Yeah, I guess so. XRX is true because each gradient is the same as itself. Good. And then you can go, therefore, R is reflexive. 1/3 done. I don't. If X are Y, then Y are X. If X has same slope or gradient as Y, then what? Y has the same slope as X. Y has same slope as X. Therefore, R is symmetric. That relationship. Symmetric. Oh, let's go for the last one. We have X, R, Y, and X, R, or X, Y, R, Z, then X, R, what? Z. So if X has same slope as what? Y, and Y has same slope as Z, then what has to be true? You got it. Has same slope as Z. Therefore, R is transitive. We have one more thing to write. Do you know what it is? One more thing to write. Yep. Since R is reflexive, symmetric, and transitive, R is an equivalence relation.